Hello, I am Daryl Haggard, and I am here to tell you about black holes. So I really enjoy some call and response, especially since now we're here coming toward the second to last talk. So I'm going to ask you questions, a few questions over the course of my talk, and I would like you to respond if at all possible. So my first question to you is, what planet are we on? Awesome. Okay, so we're off to a very good start. At the end of this presentation, what I would like you all to say to me is if I tell you that black holes are truly awesome and that they really don't suck, I would like you to be able to respond to me that black holes don't suck and really believe what you're saying. So that's my objective here today. I want you to know that black holes really, they are not cosmic vacuum cleaners. They don't go rogue around the galaxy and gobble things up. That's not what they're about, and that's not what they're up to. I would like you to think of them as very massive objects with very excellent manners. So, black holes are truly and very, very well governed by our theory of general relativity. So far, despite many tests that we have put these to, we have never seen deviations away from general relativity, and they seem to really be guided by this kind of amazing theory that governs a lot of what we think is going on with gravity. So you've heard a little bit about gravity from other speakers today, and I would like you to think now about the mass involved in black holes, to remember that they are indeed truly very, very small, but they are still spectacular. And so I'd like you to start thinking a little bit about the awesomeness of black holes in the context of this really amazing image that I think might appear, oh, that's up to me, I guide the image. Yes, okay, here's the black hole. So have you all seen this picture before? It's kind of an awesome thing to be an astronomer and have a lot of people say yes when you show them a picture of a black hole. That's a new thing that we can actually show you an image and be able to tell you a little bit about what's going on with this incredible image of a black hole. So they are really awesome creatures. This is the very first picture we've ever been able to take of the photons swirling around very close to the event horizon of a supermassive black hole. So I'm going to use this image as my prop for a minute to help you understand a little bit my favorite definition of what a black hole is. So I like this very toy model. There's a lot more complications to it than this, but think of a baseball. And what happens when I, Daryl Haggard, throw a baseball? Be honest with me. I see some people doing this. That's literally what would happen. It would just fall down, right? So the baseball, it falls back down to the surface of the earth. I'm not that strong. I've got a pretty terrible throwing arm. So this baseball falls back down because of the gravity of our planet. And so it's experiencing our gravitational pull, the planet's gravitational pull, but it turns out that if I could accelerate, just put a little rocket on the back of that baseball and accelerate it up to 11 kilometers per second, or just a little bit more, I can actually get that baseball out into orbit, or even completely out into outer space, off the surface of our planet. So 11 kilometers per second, if that's not your ball of wax, maybe you prefer Queen's units, that's something like 25,000 miles per hour, right? Our cars don't go that fast, but sometimes our rocket ships do. So the thing about a black hole is that velocity, that escape velocity, the velocity you would need to give a particle for it to escape off the surface of that body, is faster than the speed of light. So light is trapped inside the black hole, and light is the fastest velocity. Those photons are traveling at the fastest velocity we know of. It's a fundamental constant. So light's stuck in there, and that's why we call them black holes. But this image is a picture of all of this stuff just outside the black hole. Just outside the event horizon of the black hole, these are the photons and the hot gas and the hot material swirling just outside the horizon of this black hole. So let me tell you just a little bit more about this particular black hole. This one, we like to use relative units in astronomy, so we often measure things in terms of other things because otherwise the numbers are just a little bit hard to hold in your mind. So this black hole is 6.5 billion times the mass of our own sun. So that's a lot of mass, but that mass is packed into a really small space. So I'm borrowing this cartoon from XKCD, which some of you might recognize. That's a little picture of our sun and Pluto's orbit and the Voyager satellite, which is the farthest thing we've ever managed to throw out into space. And that scale is superimposed on this supermassive black hole. So 6.5 billion times the mass of our sun crammed into a space roughly the size of our solar system. That's what makes it a black hole. If that still doesn't quite kind of match your intuition, let me give you another example. Here's a really small number, relatively speaking. This is 3 millionths of the mass of our sun. Anybody know what that might be? I made you say it before. Earth. Okay, that's exactly right. So our Earth has about 3 millionths the mass of our sun, but the Earth could be a black hole too. If you could just smash everything, your mom, your dad, some of the moms and dads in the audience tonight, all the trees, all the oceans, all the buildings, all the continents, into something the size of a sugar cube, that would also be a black hole. It's not that our Earth all of a sudden sucked everything in, it's just that you compacted all of the mass down into a very small volume, and that's what gives you a very high escape velocity. So I'm just going to let us now take a little journey to wrap up my time since I'm running out. This is a beautiful image made to help you walk you into the universe where this amazing supermassive black hole resides at the heart of the so-called Virgo cluster of galaxies. So we're zooming toward the constellation Virgo in the night sky. And there's a massive cluster of galaxies. It's the nearest structure of galaxies to our own Milky Way galaxy. And in the inside of this incredible cluster of galaxies, there's a particularly massive galaxy right in the center called M87. And you can already see here that through other pictures, we can see a jet zooming out of the black hole. And as we zoom in a little bit further, we can actually see that jet structure continue all the way down toward the very, very heart of this galaxy. This jet is kind of pointed toward our line of sight, which is a little hard to make out in these images, but this is all real data zooming in closer and closer and closer until we reach the event horizon. So not only does this black hole not suck, it is throwing material and energy out into the universe at scales that are enormous compared to the size of the galaxy that hosts the black hole. Let me just show you one last little video here, which is actually going to show you the photons in orbit around the black hole, just to further make the point that not only does it not suck in mass and dust and people and astronauts, the black hole doesn't even suck in the photons. These are simulated paths now of photons in orbit around a supermassive black hole, like the one that we saw in M87. And you'll see that they're bending, just like the light through your glasses gets bent to focus on your retina. The black hole does bend the photons just a little bit due to gravitational lensing and make this beautiful ring image that we see. So it's not sucking the photons in, but it does redirect them a little bit to give us this really amazing kind of structure that we've now viewed. All right, so that's all she wrote. So when I tell you that I think black holes are awesome, you are now going to tell me. Thank you.